So thanks for having me. I will present, basically it's an overview talk about what we do, who we are, and the contributions will of course not be entirely by myself, but mainly from Benedikt Strajner, Matjaž Ličer, and some other colleagues. Yeah, so I will start with the, okay. I'll start like this, with a teaser slide. So this is really a cherry on the top, a pinnacle of how we integrate meteorological, oceanographic, and so the two modelings and also the coupling between them. So this is an on-demand application that we do for search and rescue at sea or for ecological disasters. And I will speak about this later on, while you will have to bear with me for maybe a bit more boring slides. So just to give you some hope, there'll be some more vivid slides later on. So just a quick outline. So I will be speaking about the numerical model, so either the meteorological or the oceanographical. I will be putting a lot of emphasis on the daily cycle and the time-critical constraints. So the time criticality, maybe this is something where our HPC workloads differ mostly from any others, I would assume. And then I will show you what are the current setups that we run, either in-house or in Bologna. And I will show a bit, as already Maya mentioned, about the future system, which we developed together with the National Weather Services of Austria and Croatia. And of course, I will still speak a bit about AI. In this sense, it's AIWP. So this is a sort of abbreviation which is starting to become more and more popular. It's as opposed to numerical weather prediction, the NWP. This is now AIWP. Okay, so we are, as already mentioned, from the Environmental Agency. Is this slide? It's not working. So we are in the Office of Meteorology, Hydrology, and Oceanography, and since a long time, historically, it's been that the most HPC demanding activities have been together in the Meteorological and Oceanography Modeling Division. We are a staff of 6. We have 2 SMASH postdoc students, and we have 2 fellows from Destination Earth. So 2 people employed on the digital twin for the Destination Earth on-demand extremes local simulation. This is a project by the European Commission and the ECMWF. Our main task is to port, so the biggest predator we have is the local in-house forecasting office. So either the meteorological, the hydrological, or the oceanographical forecasting divisions. And we are also providing support to the colleagues at the air quality. So similarly to what we do daily for the weather prediction, is somehow similarly done also in the field of the air quality. And we are also very much involved in the remote sensing. So we are daily in touch with the colleagues working on radar and satellite imagery. And since we are I would say the most powerful user of the HPC in-house, we are very much involved also in the HPC-related business, so also in terms of administration a bit. Okay, so we are co-developing, implementing, and operationally running a numerical weather prediction model and the ocean model, and we are taking care of some other downstream applications. And I've talked about already hydrology, air quality, and nowcasting. And again, I will emphasize here the time criticality. So we really have to be sure that we want to have the forecast ready before the weather would actually happen. So we want to be sure that we forecast for tomorrow, not for yesterday. And we have quite a lot of close international collaborations. So we are part of Accord, which is formerly known as Aladdin. And we are together, so this is actually bringing together a lot of weather services from Europe. And we have a closer collaborations within LACE. This is the Central European tighter collaboration. And we are also members of ECMWF, which is really more or less, well, leading the field globally even. Yeah, so just a brief history, because mostly Jure Cedilnik, my colleague, which some of you know him, probably would want me to really specify that we had the first Linux cluster self-built for the purpose of numerical weather prediction. One of them, at least in Europe, with 6 digital alpha processors already in 1999. Then we had several HPC clusters which were bought. Well, the second one was also self-built, but and now it's we are in the process of a tender for the next phase. While we have this in-house HPC machines, we also are entitled to have some computing power in Bologna on the ECMWF machine, and I will speak about that in a bit later, in a few moments. So the numerical model, just a brief explanation. So we take partial differential equations from atmospheric physics or fluid mechanics in case of oceanography, and we discretize in space and time on a grid. So then we get, we need to prepare the initial condition, which is itself a very demanding task, and then we march the solution forward in time, integrate, taking into account the boundary condition, which we obtain from the global models, in this case ECMWF. So just a quick schematic how this goes. The most important thing here are the observations. So without observations, there is nothing, more or less. So we start this loop. I can't show it. Okay, we start this loop with observations, which enter into the data simulation, and where it's combined with the first guess. So this is actually one of the second most demanding tasks that we do. And this is combined into analysis, which is the initial conditions. So this is actually moving from observation space to the model space. And here we are on a gridded space, so gridded analysis. Then we do the integration. This can be a short one, like here. This is the most demanding part. Well, actually, the longer integration is, of course, the more demanding, but the integration itself is the most important part. And then we do a loop back, and this is basically the so-called data simulation cycle. We do this every hour or every 3 hours, depending on the resolution. So 8 times per day, we have the model doing this, collecting observations, using some sort of variational data simulation to combine them optimally in a way that we get the best possible solution based on observations and first guess to get the initial condition in a gridded space. And then we run the production forecast at the end. Also can be 2 times per day, 4 times per day. But this is basically the input for all the other users, primarily the forecasting division, but also all the other graphics and everything. So this is done. So the analysis itself is done 8 times per day, but the production is usually done 4 times, or in case we have a shorter time span productions, we have them in between as well. So again, the time criticality, which I cannot emphasize enough. So we wait 30 minutes for the observations to arrive, not more, or in case of the rapid update cycle, which is the finer scale model, even less. And then we have to go. We have to start the process, and we at that time have to either kill or suspend all the workload that is there. So of course we don't take entire local machine into use at that time, but some of the bigger tasks that can be there will have to be suspended or killed. And then we wait, then the results will usually be available after 1.5 hours of this process. So every 1.5 hours, 8 times per day, 1.5 hours after the so-called network time, when we we collect all the observations. Usually after that time, we have some sort of solution of what the weather will be based on the latest possible observations. For this, so these are a broad spectrum of tasks which are used in this case. So I mentioned the data simulation part and the integration part, but there's also a lot of different tasks which are involved of various kinds, from interpolation to post-processing to all possibilities. And for that we use a so-called EasyFlow automatization software, which is actually able to guide us through all this. Or I mean, this is to fully automate the system, and it's able to observe to find out the errors which can occur, and to restart the tasks if needed, or to issue some messages if there's something really wrong. This was developed by ECMWF, and it's used more or less widely by all major European weather services. Yeah, now just briefly, on the left side is the most the hardest, I mean, most used workhorse, the model which we have at 4 kilometer. So this is the problem of the size of 450 times 450 points at 87 levels. And this is the one I was speaking of, so that it's 8 times per day we do analysis, and then we have 72 hours runs every 6 hours. And intermittently, we have 36 hours every 3 hours. And this is actually what's guiding most of the other model chains, either be it air quality, nowcasting, hydrology, oceanography as well. And this is actually an example from this Monday morning, when you had this, you can see this bluish color, so it's the cold air protruding from the north, bringing making the snow level height reaching the ground. And this is another example of the 1.3 kilometer model. So this is an even more demanding task. So 600 by 600 points at 87 levels. And we do this every hour with the aim to really capture as many as possible the observations on the local scale as well, so the radar too, to be able to really predict as soon as possible, even sooner than the one on the left, as the weather is going on. Yeah. So, and then in Bologna we had another 2 separate domains which we run. The one is a really huge domain here on the left side, which is this is only once per day. So this is only the orography seen here. So it's really stretching from the Alps towards the Middle East actually, and this is mainly to be used as a support for this southern and eastern European countries which maybe don't have their own numerical weather prediction systems in place. And this is an ensemble that we run together with LACE countries, so Austria, Hungary, Croatia, Poland, Czech Republic, Slovakia. And this is actually going to be replaced now with what I will talk about in a few moments. And this, on the ocean modeling side, we have the 2 ocean models which are coupled with the meteorology. So we have to provide the wind and some of the other variables to be able to run the ocean currents and the wave model. So the ocean currents on the left side and the temperature, and on the right side, an example of the wave output. So you see here, for instance, the strong, the very high. This was I think westerly situation, so very, very high waves to the south of the Adriatic. And the issue that is the most troubling for us are the coastal floods. So when we have very high levels of the sea, and this is actually where we, for some time, running a simplified NEMO, so this simplified ocean model, to be able to really use it coupled to the global ensemble, so to have several possible solutions of how the atmosphere state will look like. We coupled to this the NEMO ocean model, so to be able to really capture all the possible solutions that will come, that will happen on the sea in the Adriatic basin. Because the Adriatic basin is very prone to how the exact location of the cyclones, so the lows and the highs will be, and what will be their temporal distribution as well, because there is a resonant frequency of the Adriatic basin, and in case this is close to, so that the movement of these lows will be close to the resonant frequency, it can happen that you have a very strong response in terms of the high water in the northern part, in Piran, Koper, and Venice, for instance. Here we actually replaced this, running this ensemble with the classical model. We replaced it with Hydra 2. This was developed with the faculty, I think, with the visual cognitive system labs, yeah, exactly, from the faculty of information science at the University of Ljubljana. And this was a very successful story that we are actually, because we are not so much interested in the entire field that we would be able to get using the full model. We are mostly interested in when and what is the uncertainty of possible floods. This is why we this was really adapted. This system was really very well adapted, and is serving very well to give some hint at when this floods can occur. So this is a story where we were able actually to use the AI neural network to actually phase out the classical approach, so to say. And now we come to the initial slide. So this is an example of a surfer that was waiting for a long time until we had a really red alert for the Yugo wind, for the southerly. So because he was really keen on going to surf in the very strong wind case. I mean, I suppose it's a challenge. But it happened that he got, there was a malfunction. I think there was a sail broke, I think, or something like that, a mast broke maybe. And he got stranded at the sea. And we were actually asked to provide the possible path or possible location. So this is actually a Monte Carlo simulation, which is taking into account the currents, the waves, the winds. So you have to have really everything right. You have to have the meteorology right first. You have to use this meteorology to drive the ocean model. Then you have to use the ocean model, currents, and the wave model, waves, to use this all in this simulation to be able to somehow predict where he's going to go. And then you have this, and you have various possibilities on what kind of event you have. So it can be an oil spill, it can be a surfer, it can be just a person in water, it can be a container. And we provide this on demand. It can be a cadaver, and then we do a back-in-time integration to see where it might be coming from. And in this case, it's interesting that he got out a bit more to the east, so more to Sicilian, not so much to where this would not maybe to Grado, where this would somehow implicate, but this is because he was active on his board, so he was paddling towards east, towards the coast. So this has not been taken into account in this simulation, of course. Yeah, but we do this regularly in case we are asked by the authorities, or we can do it ourselves as well, of course. But so far, except for, it's mainly been used for some exercises, luckily, in case of oil spills, for instance. Okay, and now about the future. So we want to have something like an ensemble forecasting system for the local scale, for the kilometer scale. So something which maybe you know from the predictions of hurricanes. It can be seen in public media as well. So you have these cones of probability where the hurricane will go. This is on the bottom left picture. And we want to have to go towards something like that for storms on the local scale or for hail. So this will help. This will bring us uncertainty. So uncertainty estimation, but also it will enable to have the so-called flow-dependent data simulation. So to be able to really estimate exactly how do the observations behave in the model space given the exact situation now. So flow dependence. So it means that if you have strong, I don't know, southerly winds, that the observation of temperature in the peak, in the jet of this wind will be mostly, I don't know, carried towards the northeast and not so much toward the northwest. This is now not taken into account as it should be, and it's as we hoped it's going to be in the future. Given so, I don't know, probably I have not so much time, but the idea is that you are doing some sort of perturbation of analysis and of the initial conditions, basically. And you use this, all of them as an initial state for each individual forecast, and you will arrive to different kind of states in the future. And based on that, you will have a sort of probability for all the possible events that can occur. And just one example of a case of a hail in this autumn. On the right-hand side, you see the radar image. So these are the two different times. This was at 8 and at 9 p.m. On each row. So the first row is 8 p.m., the second row is 9 p.m. And you have an example of how this system is better able to capture the initial evolution already of the storm cloud. So in the first column there is the regular approach, so to say, and in the second column is where we actually use this flow dependence to be able to better estimate or to better analyze where this system already is and where it's going to be in the next hour. And now for the future AI ML, this is a work of Matjaž Puch, our SMASH student. And so we would really like to see, if possible, that the integration part of the model would be replaced with an AI ML emulator. And there are some large challenges actually here still. So basically from how exactly to couple the global grid to the local grid. And this is actually an example of this, because the fact that the inference of such a model is actually very cheap makes it possible that you do in one go the global and the local model. And these nodes here, which you can be seen on the bottom picture, are actually the nodes from the globe in the graph of the neural network from the global model. And in the left top corner of this picture, where you see all black, is because there are so many nodes there that it's all black. And this is actually the target domain of where we want to predict. So this is an example where we tackle the global and the local scale in one go. And we would like also to bring some added value in this, to be able to not just do the data simulation as we do it now, but also to use the observations in the part of the running of the AI network. And this would also enable us to have the most possible frequent inferences possible. So really to be able to run the model as soon as the first new observation comes in. So to have even more runs all the time, to have, as soon as you have new information about the temperature somewhere or about the radar image somewhere, to start an inference. This would even have more runs then, which would need probably to do some further analysis of all the possible scenarios, so to have some sort of automized interpretation of that as well, which is not the case now. Okay, thank you for your attention. I'll be happy to answer any questions.
Thank you very much, Jure Cedilnik from the Slovenian Environmental Agency. We have time just for a short question because we already entered into the time aimed for a break, for a short break. Any arms there in the audience? Otherwise, I recommend if you have any questions for Jure Cedilnik, you just stop him during the break and ask him. I'm sure that he has many interesting data and things to say. Maybe just very, very tiny one, a very lay one. Is it going to snow tomorrow?
Yeah, well, not in Ljubljana, I suppose, because it's maybe initially, but then it's going to be higher up. So
okay, so we have to climb to the mountains then. Yeah. Thank you very much, Jure Cedilnik, and I wish you a pleasant break. Now it's time to I don't know, to stretch your legs, to grab a drink, to catch up with colleagues, and we meet again here in half an hour. So.